some conflicts and different things going on from supercomputing forward. I think is just before supercomputing was the last meeting that we had, and so we have a bit of backlog now of some things that we're trying to work through. So we picked some of those today. Jared has been working on part of a theme that we've been discussing in Hi-Hat of essentially looking not just at individual invocations, but at graphs. And NVIDIA came up with something called Cuda Graphs, which we've reviewed in the past. If people missed that, you can go back and some of the older materials, and you can find something posted on that. And we've also discussed here how we've layered some different ways to get down to graphs on top of that. And we've started looking at executors. In the grand scheme of things, we're looking at sort of generalizing executors so that you can have multiple backends. The first step towards that is doing C++ executors on top of a single backend plus those Cuda Graphs. That's what Darren's going to talk about. We've also been looking at Cuda Graphs and other graph-like constructs in the context of some other contexts like OpenMP tasks, which Tom is going to talk a little bit about, and OpenACC, which James is going to talk a little bit about today. And we'll wrap up. There was the Exascale Computing Project, or ECP, has an annual meeting that happened back in January. Where we didn't have a meeting in January because we're still doing that. And at that point, we gathered a bunch of people with some common infrastructure interest in common interoperable infrastructure, and give a little bit of an overview at the end about that we went through, and posted the link to the slides in the presentation thing. So Jared, if you'd like to go ahead and get started, that'd be great.
Yeah, you bet. My slides are visible. Can you see these slides?
Yes, we can.
Great. So, right, as CJ was saying, I've been exploring this C++ executors proposal in the context of Cuda Graphs, and been collaborating with Jeff Larkin here at NVIDIA. He's actually been working on integrating some of this work into QMCPAC, which is this large scientific application. And it sounds like maybe he's going to talk about his learnings in a few weeks. So in this presentation, I'm just going to concentrate on the C++ executors proposal and how they relate or do not relate to graph APIs like Cuda Graphs. Right, so just for a quick roadmap, if you have not been exposed to the C++ executors proposal before, I'm just going to give a quick review of that to get people on the same page. I want to talk a little bit about the goals of this exploration, and then two specific types of executors that we've prototyped over the course of this project, namely this kernel executor and this graph executor. And then I'll conclude with some what I think are opportunities for enhancing both Cuda Graphs and our executors proposal. So the idea of executors, right? So say you're building some sort of library like the C++ standard library, or maybe some sort of library for doing, matrix algebra. You've got a number of entry points to that library, like sorting functions, or maybe an SGEM matrix multiplication function. And then there, down at the bottom of the screen, we want to hook up the implementations for functions like sort to resources like GPU runtimes, or OpenMP, or thread pools. And if we just do that sort of naively, we've got this multiplicative explosion in the middle here, right? Because we've got an implementation of sort for OpenMP, and then we've got one for the GPU. Maybe we've got a SIMD implementation, and that's just really hard to manage. So what we want to do with executors is interpose a middleman, a sort of uniform API that each of these entry points, these algorithms, can target a single uniform abstraction instead of this diversity of interfaces there on the bottom to avoid that multiplicative explosion. So that's what we'd like to do with executors within C++. So you can think of executors as sort of like allocators for threads instead of bytes. If you allow yourself to be a little loose about how you'd like to define the word thread. But the idea is that programmers need to control where applications execute, because locality is totally critical to performance these days, right? So programmers need a way to say, execute this on this GPU or this CPU core or on this NUMA domain, and that's how we'd like to present these things to the programmer, is through this executors abstraction. But not only do they need to talk about where things execute, I think that programmers would also like a sort of a nicer API or interface than what we currently have today with, last slide, we have this diversity of different interfaces that are totally different from interface to interface, and that's very complicated. So if we introduce executors, the idea is that with a single API, namely executors, could help programmers organize the code bases that they work on. So that's executors in a nutshell. What we wanted to do with this exploration was, as I was saying, explore executors in the context of these graph runtimes, especially Cuda Graphs. We want to figure out if we can target these sorts of APIs, these sorts of graph APIs from the proposed executors API. And to do that, we wanted to explore executors within a large application. And the one that we've been working on is QMCPAC, which is this open source quantum chemistry simulator. Jeff Larkin has been doing the work on that. And something I was interested in was exploring this senders and receivers proposal, C++ proposal. Basically, it's a proposal to do lazy execution on executors as opposed to more eager execution. If you're interested in the details, you can find a proposal at that link. But it seemed to me like the senders and receivers proposal seemed like a good fit to Cuda Graphs, because Cuda Graphs is a lazy API where you're sort of defining your work in one step, and then in a second step, sort of releasing that work to be executed. So I thought this would be a good opportunity to evaluate that particular proposal in the context of something concrete like Cuda Graphs. As a non-goal, I did not want to focus on the design of like an explicit graph abstraction. I just wanted to focus on executors, Cuda Graphs, and the senders and receivers stuff. So in this prototype, we built two executors. The first is this kernel executor, and it basically just wraps up traditional Cuda kernel launches. So if you're familiar with Cuda, you remember that we have this triple chevron syntax that launches a kernel. It basically just wraps that up and puts it behind this executor interface. And this executor is eager. And by eager, I mean that once I have told my executor I have this kernel to launch, there's nothing else I really need to do to make the executor launch that kernel. There's no second step to execution. It sort of eagerly consumes that kernel and submits it to the Cuda runtime for execution. And then in addition to this kernel executor, we also built a graph executor, which instead of being implemented with these traditional Cuda kernel launches, we've implemented with the Cuda Graphs API. And along with this graph executor, there's this associated ensemble of these so-called sender types, which you can kind of think about as futures, if you're familiar with futures and promises. And unlike the kernel executor, this executor is lazy. So we actually separate the step of defining the work we want to do from actually submitting it to the runtime to be executed. So it's a sort of a natural fit for Cuda Graphs. So this is how one might use the first executor, kernel executor. Remember, this is just abstracting kernel launches. So the first thing someone might do is to create one of these Cuda contexts just to act as a home to own resources that the kernel executor might need to allocate. as a side effect of launching these kernels. Then assume that we get some CUDA stream for somewhere. And then to create an executor, we pass the context and the stream to get ourselves an executor. And then to launch a kernel, we use this API called bulk execute, and it has a number of arguments that I'll discuss on a future slide. But we're basically simultaneously describing the work and then executing it with this bulk execute call. And then to wait for all the work that we've submitted through the executor to finish, we can call this .wait function. So it's sort of a fork join model here, where we're forking off work through this executor and then joining it through this wait function at the end when we're ready to wait for our results. And then the details of that bulk execute call. So this is, we're launching a CUDA kernel, so we sort of describe the number of thread blocks and the number of threads per block in this shape variable, which has this type, this grid index type. And then to launch a kernel through this bulk execute function, I've defined it in this slide with this lambda function. You don't have to do that, but it's kind of convenient because we can do everything in line. But that lambda function takes this grid index to identify which CUDA thread is going to execute the body of this function. You can see that inside the body of this lambda, I've picked out the block index and the thread index from that composite index variable. And then I just use that to print out a message using printf, just to identify myself, whoever is looking at the terminal. And then what goes in these extra parameters are some extra functionality that I didn't actually use in this example. But these two additional lambda functions we call factory functions. And their job is to create variables that get shared amongst all the threads participating in this bulk execute. So this first lambda function is going to return the value 42. And that's going to create a single variable that all the threads in this kernel launch are going to share. And that gets hooked up into the lambda function in that grid shared variable there. And then separately, I have this other factory that's going to return the value 13. And instead of creating just a single variable that all the threads are going to share, it's going to create a variable per CTA, or per thread block. And then all the threads in that thread block are going to see this same single shared variable. And that gets hooked up into the lambda function in that block shared parameter there. So this is just a convenient way to allow the threads that are going to execute this kernel to basically communicate, right? They can communicate through these shared variables, and the executor is responsible for putting those variables in a place that's sort of local to the threads that are going to be sharing and communicating through them. So for example, the grid shared variable would go into global memory that's sort of dynamically allocated through a function like CUDA malloc. And then the block shared variable is going to go into that special on-chip shared memory that you can sort of configure every time that you launch a kernel. So because the executor has sort of information about where it's executing and how the threads are organized, it has the smarts to put these variables in an efficient place. So that's the kernel executor. It's basically just wrapping up the traditional CUDA kernel launch. So next, we built this graph executor type that's going to target Cuda Graphs, and I've got some example code on the screen here. What's different about this executor is that we're actually going to explicitly tell it about dependencies between tasks that we create, right? So like before, we get a CUDA stream from somewhere because we're going to, the executor is going to launch all of these, all the work it creates on a particular stream. And we can create a graph executor from that stream. And then to set up sort of the description of our task DAG, we're going to connect these things called senders together. They're called senders because they're supposed to sort of send results from one task to the next. And so to set things up at the beginning, we need a root for our graph. And I've just named this void sender because it's not going to send a value anywhere. But this is going to basically be the starting point for our graph. And then we can actually create work that depends on that starting graph, as we do in this second line here, where I called bulk then execute on this executor. And one of the parameters that I pass to that is its predecessor node. In this case, it's that root node, which means that the idea here is that when the work at the predecessor node completes, then the work that I'm describing through the bulk then execute is sort of released to be executed. So we're actually explicitly describing the dependencies between tasks through these senders using the executor. And what I get back from this bulk then execute call is this thing called a kernel sender. It's basically going to describe a kernel launch that depends on that root node. And then say I only have a single kernel launch as I do in this example. If I want to actually submit the kernel for execution, that's a second step that I call with this .submit, call. It's basically going to prepare the graph I've described for the Cuda Graphs API, communicate everything to Cuda Graphs, and immediately execute the graph that I've just described. And then if I want to wait for the entire graph to complete, I can take that final sender object and then call this sync wait function to basically block the calling thread and wait for the kernel to finish. So it's still kind of a fork join model like we saw with the kernel executor. So you can sort of think about the graph executor as a factory for these sender types. Each method of graph executor produces a different type of sender that can target sort of a different type of node in the graph that we're going to describe to Cuda Graphs. So for example, the kernel sender internally is going to call this Cuda Graph add kernel node to tell Cuda to add a new a kernel node to the graph it's constructing. And similarly, the copy and host senders add memcopy and nodes that tell Cuda Graphs to execute a function on the host. So we have this zoo of sender types that basically target different types of nodes in the graph. And you can imagine as different node types are introduced to Cuda Graphs, we can just target them through introducing a corresponding type of sender because they just represent nodes in a task graph. They're basically our stand-in for mediating dependencies. And as I was saying before, the reason they're called senders is that if these nodes produce results, then those results get sent down to any children that depend on them. And of course, senders are lazy because the way the describing the tasks that we want to create is separately from actually submitting those tasks to get executed. Right, so lazy execution is all about separating the work description from submission, because the actual submission part of it may require acquiring some expensive resources, and you don't necessarily want to do that for every step of your description. You want to sort of save all that for the end and acquire those resources in a separate step. So it basically proceeds in 2 stages, and I put a star there because Cuda Graphs actually proceeds in something more like 3 stages, and I'll talk about that a bit later. But the first stage is this description phase where we're talking to the executor through functions like bulk then execute to describe the tasks that we want to execute, and it basically each one of those calls consumes a sender and then produces a sender that I can use as a parameter to some next phase of the task. And then finally, when I've described everything with the executor, I can submit the work for execution by interacting with the sender through .submit. And basically what that is doing internally is it's going to traverse this DAG of senders that I've described and communicate the details of each one of those nodes to the through the Cuda Graphs API. Then it's going to take that description and actually go into the second step to instantiate the graph. And then finally, it's going to launch the graph. And those are those 3 stages that Cuda Graphs expects on the bottom there. So it's not a perfect fit, but it's doable. So this is just an example implementation of one of those executor functions. We called it host, then execute. It's just going to enqueue a node that's going to execute on the host. So the way it works is that this function host then execute takes a function to call on the host at that node, and then some predecessor object that function depends on. That's described as a sender. Inside here, I'm going to create a Lambda function that's going to basically package up any parameters from this node and return this special type that the Cuda API expects when describing the node. And then I just finally create one of these host sender types. I tell it which stream it's going to be running on. I give it this parameters function, and then I take the predecessor and give it to the host sender. So that's the sort of the first step where the graph executor is, describing the DAG through these senders and functions. And then you can take a look at the implementation of one of these host sender objects. The primary thing of interest here is this insert method, which takes a Cuda graph and it's going to basically insert itself into that graph. To do that, I need the predecessor that I depend on, and I need those Cuda host node params, the special object that the Cuda Graphs API expects. So I can, it basically works, insert basically works recursively. It takes its predecessor and tells its predecessor to insert itself into the graph. And then it produces this Cuda graph node object that I'm going to give to the API later. Next, I take that node params function, call it to actually generate the parameters for this node. And then finally, I can introduce the host node, talk to Cuda Graphs through this Cuda graph add host node call, and basically describing how the node relates to its predecessors, and I give it the node parameters. Then I finally return the Cuda graph node that this call produced. So anything that depends on this Cuda graph can use it, or this Cuda node can use it in its insert call. So the whole thing kind of proceeds recursively as we're traversing this graph of senders through this insert function. Right, so once we build that, first thing I did was to see if this API introduced any overhead over just raw Cuda kernels or the kernel executor implementation. So to do that, I looked at the bandwidth of DAXB on a Titan B. If you're not familiar with DAXB, it's just vector addition. I assume everyone's heard of it before. But you can see that there is actually some overhead here that the graph executor is producing, because we've got this gap at small array sizes between the graph executor and all the other implementations which are performing at roughly the same performance. And the reason for that gap is because, as I was saying before, Cuda Graphs actually has 3 stages, but the sender's proposal I was targeting only has 2. So there's an additional stage that Cuda Graph that's involved with Cuda Graphs, where we're actually instantiating the graph before we execute it. And that's kind of an expensive call, and that explains this gap here. But you can see for large problem sizes, it's not very significant, but it's something that we have to care about for smaller arrays. And there are simple ways to work around this. The one that we tried was just to minimize the graph instantiation, and that eliminated the performance gap. Though it did produce kind of an awkward implementation, but in the end, we were able to match, get all the performance of all these different implementations to match. So the upshot is that this overhead, there's a simple fix for this overhead, but a naive implementation, you'll definitely suffer this performance hit. So in conclusion, we took a look at Cuda Graphs and Executors and how they relate, and found some enhancement opportunities. With Cuda Graphs, something that's sort of limiting us from actually implementing a full-fledged executor implementation is this problem that the Cuda Graphs API presently has no first-class support for memory management. So if you need any sort of dynamic memory allocation, you have to do all of that out of band on your own, which is a little awkward, let's say. And I actually think Cuda Graphs could probably exploit some performance opportunities if you were able to describe your memory needs more explicitly to the API. Secondly, there's no way to have what I'm going to refer to as deferred parameters with Cuda Graphs. So there's no way to launch a kernel, there's no way to describe a kernel launch without presenting the parameters to that launch at description time. So there's no way to sort of defer the values of those parameters until later when the graph executes, which is actually kind of important, right? Because the entire purpose of describing these tasks as sort of data flow DAGs is so that data can flow between different nodes in the graph. We can't do that at the moment with Cuda Graphs, and these two limitations lead to a lot of out-of-band communication, which I suspect may be a performance pessimization, because I think Cuda Graphs could exploit that information, and it also leads to sort of an awkward code base where we're sort of having to explicitly manage the memory ourselves and then sort of shoehorn it into our graph. So I think we could enhance Cuda Graphs, and at the same time, I think that the senders and receivers C++ proposal I mentioned before could also be enhanced, primarily because it has this two-stage approach where you first describe the work and then submit the work. But for a system like Cuda Graphs that expects 3 stages, where there's an extra instantiation step in there, it's kind of awkward to target that. And I think if there was more first-class support for sort of a finalization stage before submission, we could actually, I think performance would be a bit better. It would give users a bit more control, and it just wouldn't lead to kind of an awkward implementation. Secondly, there's no explicit support for replaying a graph in this proposal. One of the primary purposes for putting all this effort into building Cuda Graphs is that we want to describe the work once and then maybe execute the work multiple times, right, to amortize the cost of the work description. But there's nothing, there's no first-class support for that in this proposal. It might be interesting to see how that would fit in there. And then finally, there's a second portion of the senders and receivers proposal that I didn't talk about today called receivers, which I did not find a use for in this exploration because it wasn't really clear how I would use it. So I think a bit more work or a bit more exploration on my part would probably be useful there. So that's all I have, and I'd be happy to take any questions if we've got time for that.
Hey, go for it if somebody has something to raise. Nice piece of work, Jared. Do you want to comment on availability of the code?
Sure. So we're going to open source it real soon now. Probably put it on GitHub, and I'll let CJ know, and he can let everyone else know. I would expect it to go up this week. Might be useful if you're interested in the details of implementation, if you're building a similar system, just to see how we did it. Might give you some ideas for your own systems. It's definitely not production.
Tom talked, but he was looking forward to that, I think so. Good.
Mm-hmm.
Once you have it on GitHub, I can connect it to the wiki so as people can find it easily. So just CJ, if you want to send me the link to the Git, I'll enter it there.
Sounds good. And I'll add it to the, I made mention of forthcoming open source code in the minutes, and I'll add the link there as well.
Great.
Okay, if there are other questions, go ahead. Otherwise, James, you're up.
I think I'm supposed to be up next to talk, but I need to go take care of some contractor work here. So if there's something else you can do, that would be great.
Okay. Tom, do you want to go?
Yeah, sure, I suppose. I mean, I don't have any specific material to present. The main thing, I guess, was to discuss how we're looking at leveraging or working with these kinds of systems, much like Jared was talking about dealing with C++ executors in the context of OpenMP. And that makes for kind of an interesting question, because we're at once looking at how to have OpenMP work with C++ executors and vice versa, as well as how they both might work with graphs. Some things that have come up, and James has a nice example of this, is that the model that Cuda Graphs likes to use of recording a session and then playing it back repeatedly, if written directly the way that Graphs normally does it, ends up looking very odd in the programming model. Because it's a significant refactor to essentially move everything out of the loop to record it and then run through the loop replaying it. So some thought needs to go into how we can actually wrap around that. And I think James has some ideas here that I'll let him get to when he comes on. But I think the biggest thing we're looking at right now is how we can create an interface that lets us have a reusable task of some kind and apply it in the context of graphs, so that you could have a reusable task and then a reusable series of tasks. But a question that I have actually for folks who are on this call is, if you've played with graphs or other things in this area, managing updates of parameters has been an area of concern and interest for us. Have folks found any mechanisms that they like for dealing with that?
Is Stephen on the call? He's not on the call.
No, he's not.
I would encourage you to defer that question to the future.
Fair enough.
When Stephen is available.
Maybe I'll try and prod him next week. But as a general question, I mean, even outside of graphs as an interface, it's kind of a tricky problem.
Right. So LAMs give you a way around it by giving you a way of deferring when you get access to those things. But then you're still stuck with the problem of maybe your graph wants to capture the values at some point, but then update them later. And then you're still stuck with levels of indirection. But if you can keep a handle on your arguments, so you can just rewrite them in place and then have your graph read them from this side table or whatever it is the best thing that I've come up with for how we're going to do it in OpenACC. Because of course we need to, like you alluded to the fact that I have an example I can show here where I've convinced other members of the OpenACC language committee that we should look at doing graphs via the kernel's construct in OpenACC And then we would want to be able to reuse that graph, and we have the same problem. How do we update things? But because the compiler's doing everything anyway, it knows where its arguments to that graph would be, so it could repopulate them relatively easily. But I'm still not sure how well that interacts with anything other than Cuda Graphs, and I'm not sure how well it works with Cuda Graphs, to be honest.
Right. And it makes for a funny question, because actually Jared mentioned this as well. Sometimes you want deferred parameters, sometimes you want immediately evaluated parameters.
Right.
Sometimes I'm not even sure what I want. And building a one-size-fits-all interface for that seems like it's going to be one of our bigger hurdles. But
so deferred, I think, my personal opinion, deferred is always if you have to go for a single solution, deferred is a solution that gives you the most readily available solution that fits everything. Because if you have an immediate thing, you can still stick it in a deferred argument and just never change it, and it's still there, it's available. Of course, you miss opportunities for optimizations if it's deferred, because the graph compiler doesn't know that it's actually something that will never change. But that's maybe something that you have to live with for a nice interface, is some loss of opportunity, at least near term. Maybe at some point the graph compiler can figure out, can be told that, hey, this thing is deferred, but once you get a hold of it, you can use it because it won't change. Because I guess there's mutable and immutable deferred things, if you want to look at it that way.
sure.
Let me see if I can figure out how to. Where did? Sorry, I'm trying to find my. Let's see if this works, because I'm just. Can people see what I'm sharing here? I'm going to steal this away from Tom and switch over to something else, and we can continue his questions as I move forward with this.
Mm-hmm.
Just because it's got examples.
Yes, your screen's showing.
Examples would be
All right.
really helpful.
All right. So I'm just going to run through these slides because basically Cuda Graphs exist. They exist to solve a problem. They have a nice interface. If you like API interfaces, they build graphs. You can do the stream capture where you actually say, I'm going to use regular Cuda, but I want you to capture that Cuda and build a graph. And that's actually the mechanism that I exploited to prove that I could do something with OpenACC. So I wrote a really simple runtime thing. I'm going to call it a library because it's really, that's all the code right there. And it's just a way, so I have a set of interfaces that my OpenACC can call into that is compiled with Cuda and has a Cuda capabilities available to it. And it remembers the graph and everything, so it can instantiate and build the graph without the OpenACC having to change that much. So what I did is I took a simple stream benchmark that Barcelona had originally done in OpenMP with tasks and parallels and done a bunch of experiments with, and even wrote it in Cuda. And I rewrote it. There's a bunch of stuff around this loop, but basically it's an ACC parallel async. So this is a straight line graph, so not interesting graph, I admit. Straight line, there's no branches, and there's nothing all that interesting. But what I can do very easily is wrap that with get the stream, I'm sorry, I just hit the wrong button. Get the stream ID that Cuda has associated with, or get the stream, Cuda stream I'm sorry, I need to slow down and say this so you guys can understand it. Get the stream object from the OpenACC runtime that is associated with the OpenACC stream 1. So this is giving me a Cuda stream back out of the runtime. and then I can say capture that stream, pull the entire loop body of the K loop inside of there. So this is nothing different than what Jared was showing in other things. It's just that I'm using OpenACC to do it. And then I guess I didn't copy in the instantiate here and then launch it. And I can launch it over and over and over and get the correct results. The reason I did this was to show the stream on the left. It takes about 0.04 seconds for the, just slightly smaller than a gigabyte of memory versus the 0.0014 seconds when I have a graph. That's why graphs are interesting to OpenACC. That's why their graphs are interesting to OpenMP. Is overhead for tasks has always been a problem in OpenMP. People say that tasks are useless in OpenMP. One of the reasons they say they're useless is the overhead is so high that you don't get any benefit out of them. This shows with a simple graph, I go from one level of performance to another very easily. Like I said, it was literally minutes of work, maybe a half hour of debugging my code to get that performance change. And my proof of concept says that I can do it with OpenACC relatively easily. I can probably convince the OpenACC compiler team, at least at PGI, to do some tricks with a kernel's construct. The problem is OpenMP. OpenMP has no way to get the stream out. So what I just showed in OpenACC, I can't do in OpenMP today. Tom and I are working on solutions. Tom has proposed a change to pass in a stream, a CUDA stream, and say, use this stream for this dependency object. He also has a proposal in place to say, this is the dependency object that I've told you to use. Now give me the stream or streams that you've associated with it. So we can start talking about it. But it's still, OpenMP is still a ways out. OpenACC, we can prove that it works. We're starting to try and push forward with it. Okay, if OpenACC were to do this, what can it do? And we can, I think that's the last one I have. Yeah. So back up here again to this slide. You could envision a change to the code on the left there. Rather than saying anything with these directives, so put a single directive outside the K loop, and that directive would be something like ACC kernel's graph loop, and that would tell the compiler, or maybe not even needing that extra bit, tell the compiler, create a set of kernels for this loop. The kernel's construct tells the compiler to do all the work anyway, so the compiler can look at it and say, hey, there's a bunch of subkernels I can do in here. I could build the graph. I could memorize that graph. Then the only thing it needs to know how to do is how to deal with the parameters that Tom was just asking about. How do we pass in deferred parameters? How do we deal with the fact that the set of parameters might change every time I encounter this loop? But if we know that it's never a loss to do this, then the compiler could just always, when it does kernel's constructs, if it sees that it's going to do more than one kernel out of this kernel construct, it could build a graph and use that graph every time it hits the code, and greedily assume that every time it sees a kernel's construct, you're going to call it multiple times. If it's only a minor loss when you only call it once, and it's a win or no loss when you do reuse it, it becomes a wash win for the OpenACC compiler, and it's free. And that's where we're headed in OpenACC versus OpenMP, and I think it's a interesting location where we actually can probably relatively easily, without even changing the specification for OpenACC anyway, start exploiting Cuda graphs and any other graph that we could ever target. So if OpenACC were ever targeted towards hi-hat type graphs, it would just be able to do it. And that's all I had. If people have questions, comments, go ahead. And we can go back to Tom's questions if you want to ask, if you have other things, Tom. But
well, so I mean, the main thoughts that I had and kind of wanted to bounce off of people, actually, given your example, might be a good way to go from there. Is, as you mentioned, we've talked about having a couple of different ways to work with streams with OpenMP.
Yep.
The initial one was to try and get as close to what OpenACC has as is feasible in something that cannot express all of its dependencies in terms of a stream. Because OpenMP has to have host tasks in the graph, the stream doesn't encode everything. So it gets a little complicated. But passing in a stream or a native queuing object of some kind is seemingly, at least for the committee's end, a lot less controversial. So we're looking at doing that. And I would be interested if anybody sees an issue for what their use cases are with that. The other thing that I found really interesting when you brought up this example yesterday, James, is if we actually build in something like a graph construct that can then contain regions for OpenACC, OpenMP, for whatever.
Right.
We have an interesting opportunity to have that naturally do the argument updates for us, as long as we can implement it in terms of whatever the Graph API gives us.
Right.
Actually, that's the bigger question, is do we think that a compiler could implement the semantics of the first private immediate capture that we normally get for a target or a task?
That, for graphs, would not be a problem. If we know that, again, it comes back to that, how would it do it? That's where I was thinking about these. If you always assume deferred arguments, the first private things you'd want to say are deferred arguments, because they can change every time you use the graph, but they're private to the nodes as far as the graph is concerned once they're there. So there are things that you have to have special locations off someplace to stick it into. Whereas there's also those objects, like in my example here, C and A, those deferred things are actually going to point back to some global thing that you're going to modify.
Right.
And those can't be first private. And so it always comes back to when I think about it in terms of what the compiler would do. The compiler is going to build this graph. It's going to know all of the arguments that go into all of the nodes in that graph, and it's going to link them back to a side structure, which is all of the deferred arguments, where it's going to stick its data that feeds directly into the graph. And I can see doing that with the compiler, because that's really exactly what the compiler does for tasks today anyway. It builds a side structure. Okay, it's the task with the data hanging off the end of it. And that data is the first private variables and all of the pointers to the shared variables that that task is going to modify. And it can very quickly move. We can take that same structure, stick it into some sort of graph system. But then what we need to do is gather up all of those argument lists for all of those tasks and push them out to a single location that the compiler can populate, so that when the graph is instantiated and run, it grabs all its data from the side table rather than reaching all over the world to try and work. And that gives the compiler enough control that it can also help marshal data and move it where it needs to go. So if it needs to do data movements for a GPU, it can do that. And then in that side table, it just puts what would come out of the present table. This is the address that you use when you execute. You know, I wish you guys could see my hands fly, because I talk really a lot. My hands moving a lot when I just describe what I just did.
Right.
But no, I really think the graph API that Cuda has defined, the compiler can actually target it and do quite a bit. It's not as, what's the word I want here? The compiler has to do a lot of magic that the user won't have control of. Jared's stuff for C++ programmers is probably going to give better performance most of the time. I won't guarantee all the time, but most of the time, because of the level of control the programmer has. But if the user wants the easier interface of directives, the compiler can do so much of what you see in the Cuda Graphs anyway is cookie cutter code. Let me go back here. You have building all of these graph nodes, linking all the nodes together. That's really tedious stuff that the compiler is good at. That's tedious things are oftentimes the compiler is really good at that stuff. And so once you tell it that this task is a graph node and this task is a graph node, I think in OpenMP we can build very interesting task graphs, and we can expose them to systems like Cuda Graphs or hi-hat graphs or whatever graph you want. We just need to add the structures to OpenMP that we need. OpenACC, on the other hand, because we have the kernel's constructor ready, the compiler can readily just do it for us. All it takes is manpower to teach the compiler to do that. I'm continuing to work with PGI to convince them to at least prototype something there.
It would be great to see that. Actually, the one piece of OpenMP that I'm materially worried about in terms of figuring out how to deal with it in terms of the current API is when we have a graph that has a task that has a target region in it.
Right.
What in it?
Target region or update or anything that touches the device.
So that's the power of OpenMP, is the fact that you could have a single task graph that has both host and device target or device tasks. And you can take it one step further where all of the nodes in the graph are actually host nodes, but as many of them contain subgraphs, which are actually device graphs.
Right.
And
that graphs does
could be tricky.
Pretty well, right? I mean, you can intermix host and device stuff, which is great. But as soon as we have device stuff in a host graph node, we have a model mismatch that I'm not sure how we get around as of yet.
Well, as long as the let's talk graphs and subgraphs, because that host node that contains device stuff basically is just a host node containing a subgraph.
Mm-hmm.
And what I think you're saying is you're worried about the fact that subgraphs information is not exposed to the parent graph. It's kind of a hidden blob of execution, which is basically what a host node is anyway. The node has data flow coming in and data flow going out, or however you want to represent it in your system. And what happens internally is a black box. And if that black box happens to go off and touch a device, so I think I'm missing something on what you're worried about.
Sure. So that's kind of expected that you'd have a black box there. The issue is more that, as I understand it, a host task executed by a Cuda graph is explicitly prevented from doing anything device related. And I'm going to have to ring off here in about 5 seconds.
What?
We should probably wrap up. So maybe just make a couple forward-looking comments. We were going to talk about the ECP stuff today, or I had it queued up, and that's easily deferrable, so we'll cover that next time. I think we plan to meet next time on the 23rd of April, which is not our normal weekly slot, but that's our plan. Let us know if that doesn't work for you. Jeff will talk more about what's going on with QMC Pack. We'll plan to have Wojtek talk more about what's going on with Cuda Graphs, hi-hat graphs on top of Cuda Graphs at that point. And I think it'd be great, to dig more into some of these discussions. Tom, as your work matures, and James, as your work continues. So that'd be great. Do you, Wilf, do you want to say any more about the logistics?
Had to come off mute. Yeah, I did send out a note canceling future meetings for Hi-Hat, because I think we were noticing that some of the meetings in your calendars had become disconnected from the master calendar, and so when we were moving things, people were not seeing the move. We'll send out, if you could look through your calendar and see if there are any future meetings there that did not get canceled. When I cancel those, please remove them so as there's no confusion. And the end of this week, we'll send out a new series that hopefully will link to your calendars, and we can remove them when the meetings are removed or move them. So hopefully that'll be helpful. I did in the invite for this meeting put an update capability. If you want to update your information in the database that we send out, you can click on that and get an update. And please just send me email if there's something else like people have moved and need to be reconnected again. They can send me email or go out to the Hi-Hat website. So hopefully that gives a bit of background, and we'll get new invites out shortly. That's all I have.
Okay.
Yep. Cool. Well, thanks.
Right, thanks very much.
Yep. Good meeting.
We'll talk to you. Bye-bye.
Cheers. Bye.
Bye.